Okay, so this section is basically going to be a whole bunch of iterated double integrals over rectangular domains, just to give you an idea of what this actually looks like computationally. So let's take the first one. We have an integral from 0 to 3 of the integral from 1 to 2 of x squared y dy dx. Okay, so right now we're operating as y is the variable with the bounds 1 to 2. X squared is coming along as a constant. So we still have the x bounds, 0 to 3. And then we're going to get a half x squared y squared, because we took the antiderivative of y and got 1 half y squared. This is going to be evaluated from 1 to 2, and the dx comes along. So this is going to give me 0 to 3 of 1 half x squared, and then 2 squared is 4, 1 squared is 1 dx. So this comes out as the integral from 0 to 3 of 3 halves x squared dx. So now we just have an ordinary integral left, right? So let's see. This has got to go to 3, so that's going to leave me with 1 half x cubed from 0 to 3, which is just 1 half times 27, or 27 over 2. Okay, so the idea here is that if I had a rectangle whose x was bound between 0 and 3, and the y was bound between 1 and 2, and this is the surface over that rectangle, then the volume of that rectangle would be 27 halves, or what is that? That is 13.5 units, right? So there we have it. So let's take a look at a couple more examples and see how this plays out. Okay, so let's say we have the integral from 0 to 1 of 1 to 2 of 4x cubed minus 9x squared y squared dy dx. So again, we're operating with y as the initial variable. So we're going to keep the x bounds, and then we're going to take the antiderivative with respect to y. So this is going to give me 4x cubed y minus, let's see, 9 divided by 3 is going to be 3x squared, now y cubed, from 1 to 2 dx. Alright, so 0 to 1. Let's see, 2 minus 1 is going to give me 2 times 4 is 8x cubed. Let's see, we have minus, let's play this out. 8x cubed, and then put the 2 in here. 2 cubed is 8 times 3 is minus 24x squared. Minus, let's see, 1's in here is going to make that 4x cubed. And then, let's see, this is going to be minus 3x squared, right? dx. Let's combine up the like terms. 8 minus 4 is going to be 4x cubed. Negative 24 plus 3 is going to be negative 21x squared dx. So now we have an ordinary integral again. So this is going to be x to the 4th minus 7x cubed from 0 to 1. Right? So this is 1 minus 7 minus 0, which is negative 6. So, yeah, pretty straightforward. Let's throw in a trig function. Okay, so we're going to take the integral from pi over 6 to pi over 2, and the integral from negative 1 to 5 of the cosine of y dx dy. So these are x bounds. We're going to deal with this as though x is the initial variable. So these constraints are moving along. This is going to give me x cosine y from negative 1 to 5 d. Sorry, that should be dy. So let's see, this is the integral from pi over 6 to pi over 2. 5 minus negative 1, I believe, gives me 6 times the cosine y dy. Alright, so we take an antiderivative of the cosine. So cosine goes to negative sine. No, cosine in the antiderivative goes to sine. So this is 6 sine y from pi over 6 to pi over 2, which would be 6. Let's see, sine of pi over 2 is 1. Or sorry, pi over 6. No, sine of pi over 2 is 1. Minus sine of pi over 6 is a half. And half of 6 is 3. So there we have it. So same basic game, now just working with trig functions. So let's throw in something here that might involve something like a u substitution. So we've got your 0 to 1, of 1 to 2, of x e to the x over y dy dx. Okay, so we can kind of break this apart, right? Because these bounds are acting on the y. These bounds are acting on the x, so I can literally kind of technique-wise make this into this. Because within the y bounds and the y integral, these are just a constant. You can always bring a constant out in front of the integral. So let's see, we've got 0 to 1, x e to the x. The antiderivative of 1 over y is going to be the natural log of the absolute value of y, and we're going to evaluate that from 1 to 2. So this is the integral from 0 to 1, x e to the x of the natural log of 2 minus the natural log of 1, but the natural log of 1 is just 0. So this is the natural log of 2 times the integral from 0 to 1, x e to the x. Oops, sorry, that's the only thing that's in the exponent there should be the x. So x times e to the x. Okay, so at this point, we're actually into not a u substitution, but rather a by parts situation. We're going to let the u equal x. We're going to let the du equal e to the x dx, right? There's a dx there still. So going this way, we go du dx is 1, which means that du is dx. Taking the antiderivative of du, antiderivative of e to the x dx, lands me with u is just e to the x. Sorry, so this should actually be dv's, right? dv, dv, and v. Right, so by parts, it says that I'm carrying the natural log of 2, right? And then I take u times v, so that's times x e to the x, which is going to be evaluated from 0 to 1, minus the integral of v du, which is dx, and that's going to be evaluated 0 to 1. Alright, so this is the natural log of 2. This is just e, right? Because this is going to be, if I kind of think about this, this is e minus 0, right? So all times that minus the integral from 0 to 1, e to the x dx, which is, okay, this is just the natural log of 2 times e minus the integral from 0 to 1, e to the x dx. Alright, so we have to evaluate that. So we have the natural log of 2 times e minus, and that's e to the x from 0 to 1. And the integral of e to the x is just e to the x. So this is the natural log of 2 times e minus 1. right? So I believe that just comes out as, well, the e's cancel, right? Negative and a negative is going to make that positive, so this is just the natural log of 2. That's it. All right, so applying by parts to a double integral, and basically you just work from the inside out. Remember that you can do some work here that would allow you to change the dy's and dx's. You just have to change the bounds with them according to Fubini, so you can actually set up things strategically to make the work easier on yourself. But there you have it. Okay, double integrals over rectangular regions.